My name is Dr. Shobhusha Sen. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, so first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bokeh is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, course objective and outcome was framed, and let me present the same now. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics, okay, is to apply quantum mechanics for learning the latest of computation called quantum computation, learn quantum logic gates. Is to, as a student, you get comprehend about the hardware sectors of your devices, okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE or IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design, and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. On the screen you can see the various modules that are present in this course, and you can also see the module that you will be starting with. We'll start with one of the promising modules of the course, as well as you can also see the topic that we will begin with. And in this particular class, whatever we will be focusing on, the related prerequisite, what is the objective of the class, and if at the end of the class you're supposed to get something from me, that is the outcome of the session. So that session outcome also you can see on the screen. Okay, hello and welcome to class 14 of my Physics 2 courses. We have been dealing with the application of Schrodinger equation. We are already in the problem 2. Problem 2 is basically a description of a junction diode problem. So what I did the other day, I have introduced the diode problem in front of you. Initially, I introduced it according to the particle electronics way. Now we'll be solving it in the language of quantum mechanics. And I can assure you, if you use your quantum mechanics way of thinking, you will see you will go beyond, you will cross some boundaries. The application of diode will not just be rectified, it will be beyond that. Many more things are waiting for you. Okay, so this is class 14 and this is myself, and in our class electron will obey the green line, that is it will show wavy nature. Wavy nature of the electron is manifested by the function psi
This is a working equation of Schrodinger. These are the operators, you know, and we'll be using this equation of Schrodinger for the purpose of the class. Okay, for the purpose of the class, we have to use the equation of Schrodinger, and this is the basic description of the problem. I introduced, I was very fundamental. I started from very basic of the intrinsic semiconductor, wherein which you describe, which silicon, germanium, where there are 4 valence electron, the concept of covalent bonding, and the concept of doping. Each dopant means you create an ion, and for n-type doping, one positive ion free electron, for p-type doping, one negative ion, one free hole. So they together, when you make a diode, according to particle electronics, there is recombination, and because of recombination process, ultimately you get create a depletion region, and ultimately it is against the electron flow, okay, or hole flow, and the device action depends on whether it will move or not. So this is something, you know, okay, the positive bias, and these are all particle electronics thinking. I have given a different angle to this idea, that is when electron is trying to move, it is facing a Coulombic potential barrier, and ultimately Coulomb potential is resulting in a hyperbolic potential barrier in front of the electron. So ultimately electron can go if it has got more energy than the barrier height, and if it has got less energy than barrier, it can't go. So in experiment, what you do, you try to help the electron. We apply biasing. So the role of the biasing is to increase the kinetic energy of the electron. If you apply V1 voltage, so each point you increase V1 means you're slowly increasing the kinetic energy of the total energy of the electron. Ultimately, it will be able to cross the junction. So that is why you get a diode characteristic graph like this one. So diode is on when you are beyond the cut-in voltage, and diode is off when you are below the cut-in voltage. And reverse bias, the opposite story. You are actually total energy is reducing because of the formula. More and more energy means less and less enable for the electron to go. So ultimately, when you work in the reverse bias condition, you work there, okay, the device is off. So basically the journey, it is now problem of whether a particle, electron or hole, it will cross the junction or not. I have told you in terms of electrons, same story is true for holes also. It can only go to the other side if it has got more energy than the barrier height. So this problem we will be solving now quantum mechanically, and you will get some beautiful results. Okay, let's solve it now. It is called one-dimensional finite barrier problem. It is called one-dimensional finite barrier problem in quantum mechanics. Okay, so we'll do it. Okay, so let me solve the problem. One-dimensional finite barrier problem. So let us have the problem. Okay. Let me switch off the video. Let me switch the camera on. You see, this is the problem. Okay. This is the problem of the diode. Okay, so you can see these are the majority holes, free holes, and these are the electrons. These are the free particle, and these are the free electrons. They can move. This is x equal to 0 is a junction. This is a depletion width. Okay, so if the particle, electron or hole crosses the junction, then you will get some current and the device will be on. Okay, and you see what the electron is facing. It is saying if you consider electron journey, initially Coulomb is helping the electron, but finally Coulomb is repelling the electron because of this formula, and this is a variation. So any electron moving with some energy E is seeing a voltage barrier. Okay, so idea is that it will go to the other side if E is greater than V0. If its energy is less than V0, it is not going to go to the other side. Same story is for holes also. Holes are moving from one side to the other. If the hole has got mass m, energy E, you see hole will also face a Coulombic barrier. If this is Zd, the charge, Zd into E by 4 pi epsilon 0 x square type of force. So you can calculate potential energy. It will be also constant. So it will. The idea is that it will also see a voltage barrier like this. Okay. So it will only go to the other side if it has got more energy than this barrier heights, and it cannot go to the other side if it is less energy. Okay. Now I will make a simplification to the problem. Far in the negative x, it is almost equal to 0. So we consider the moment to cross x equal to 0. Let us simplify the problem, because we have to ultimately solve this equation quantum mechanically. It is going to be 0. Okay, so this gradual variation of v with x we are not considering. Okay, this is, we are considering this just dropping to 0 the moment to cross x equal to 0, which is not reality. And right hand side also I consider it is fixed to v0. So this gradual variation, this gradual change, there is a gradual change of v with x. Okay, I do not consider. Okay, we do not consider this gradual change. We consider it is like a step. It is varying like this much. Okay, it is getting the like it's taking the shape of a step. This will make, this is the simplification I have been making to make our mathematical life a bit easier. Okay, and for the purpose of the problem, we will consider the whole motion as if a particle whole of mass m is moving with some energy along x direction, because whole is moving in our favorable direction from negative x to positive x. So this is the journey we want to explain now. Okay, we'll be explaining this journey. So let us see how we explain it quantum mechanically. Okay, the moment you will try to explain it quantum mechanically, what it would happen. So this is the whole of mass m is moving, okay, with some energy E, and this is a voltage barrier it is facing. So we are solving it quantum mechanically, so it will show wave nature. Let the wave nature is manifested by the term function psi 1, which is a function of x in the region p side. I call it region 1, n side I call it region 2. If you think in terms of diode, in general, any particle of mass m and moving and facing a voltage barrier, finite barrier of height v0, it is true. In the right side, let the potential energy, let the wave function be psi 2. So these are the corresponding Schrodinger equation. So now you can see, if you look at the description of the problem, this is the value of v. Actually it is varying like this much, but I consider the moment to cross x equal to 0, v is becoming v0. So v is 0, and on the right hand side v is fixed to v0. Okay, it is constant, it is v0. So if I do the problem, so it will be taking like this shape, d2 psi 1 dx2. Okay, it is like d2 psi 1 dx2 plus 2me by h cut square psi 1 equal to 0. I consider 2me by h cut square psi 1, h cut square equal to constant, maybe alpha square. Say alpha square equal to 2me by h cut square, maybe a constant quantity. So basically this equation is again becoming a very common equation to us, d2 psi 1 dx2 plus alpha square psi 1 equal to 0. Now this type of equation you have already solved earlier, so we expect you can solve this also. In this case also, if you look at this equation, we can write down this equation in this way, d2 psi 2 dx2 by slight manipulation it can be written as 2m by h cut square e minus v0 psi 2 equal to 0. Now here, from here, two cases may appear. One case is that E may be greater than V0. That means particle has got enough energy to cross the junction, that is E greater than V0. That means you are leaving here, device is on. Suppose you are doing with LED practical, LED is on. So then this quantity 2m by h cut square E minus V0 is a positive quantity, and I call it beta square. So this equation will take a form like this much, d2 psi 2 dx2 plus beta square psi 2 equal to 0, which is very similar to the equation in the region 1. Okay, so this is the equation, d2 psi 2 dx2 plus beta square psi 2 equal to 0. Okay, it is very similar to the region 1. Now another situation might also arise, which is E less than V0, that is the particle do not have enough energy to cross the junction. This is the E less than V0 case, that is the device is off. Now a diode cannot be simultaneously off and on, so we have to consider these two cases separately. So we'll also, actually this is our main focus. Okay, so we'll discuss it. So now let us solve both the problems separately. If you look at the solution of the problem, the solution of the first part of the is here first let me solve it for e greater than v0. So the solution would be like, here alpha square is obviously 2me by h cut square, and beta square is equal to 2m by h cut square e minus v0. So this becomes psi1 equal to a1 into the power I alpha x plus b1 into the power minus I alpha x, where a1 b1 are integration constant. And similar equation you will get here also, say a2 e to the power, say suppose for example c1 into the power I beta x plus d1 into the power minus I beta x. Now let me interpret the result. Now this equation is basically the equation of a wave, because you know y is equal to, if you look at this equation, y is equal to the power I kx is basically the equation of a wave moving along positive x-axis, and y is equal to e to the power, say y1 e to the power minus I kx refers to a wave moving along negative x-axis. Okay, so this means basically this equation is basically similar to this equation. So this refers to a wave train moving along positive x-axis in region 1, that is as nothing but the psi in. This is a whole wave trains are coming in, or particle wave is coming in. Second one is referring to this case. So as if particle whole waves are coming in and some portion of the waves are reflected back. So this is the, I call it psi reflected, moving in the opposite direction. Psi in is basically psi, so psi reflected is basically this much. Now in the right side, this is also a wave moving along positive x direction, because this is like this much. Okay. Now this is referring to a wave moving along plus x in the x direction, but it is moving in, okay, but this wave is moving in region 2. So if I look at this wave, so this is referring to a wave moving in region 2. So it is basically psi transmitted. Now the last one is basically referring to a wave moving along minus x direction in region 2. Now this can't happen, because any reflection, because this is a reflected wave, it cannot take place in region 2, because there is no, if there was a PNP, there is one more junction, transistor like quantity to another junction, then it can reflect. So no further reflection, so d1 will go to 0. So basically this is the case will be that of the conduct for the particles for waves coming in and going out like that. Okay, so now if therefore if you look at the problem, it is happening like this much, that whole waves are coming in, psi in equal to a1 into the power I alpha, and it is seeing a voltage barrier of v0. This is region 1, this is region 2. Some of the waves are reflected back, that is psi r equal to b1 into the power minus I alpha x, and some portion is getting transmitted through, that is psi transmitted is equal to c1 into the power I beta x. Okay, ultimately for the wave coming in, okay, for the wave coming in, I will be calculating the corresponding current density. For the wave reflected back, I will be calculating the corresponding current density. For the wave transmitted through, I will be calculating the corresponding current density. Now the ratio of the transmitted current density and the incident current density is called the transmission coefficient. That is the probability, it is the transmission coefficient. Now if it is 0, there is no transmission, no electrons are passing, no current will be there, and if it is non-zero, some electrons are passing, and we expect that is here, because we are working at E greater than V0, some current will be there. So that is the message. But the problem is that in your class I am not going to discuss E greater than V0 case anymore. I will do all those calculations, but for E less than V0, because E greater than V0 is a usual diode graph, there is nothing you are going to get new. Our main focus will be now on E less than V0, where this is the working equation, okay, d2 psi 1 dx2, you see nothing has changed in the region 1, alpha square psi 1 equal to 0, but in the region 2, for E less than V0, that is I am working over this portion of the graph, E less than V0, when the device is off, something new is expected here, d2 psi 2 dx2, which is like 2m by h cat square, E minus V0 psi 2 equal to 0. Now in this equation I am talking about E is less than V0, so basically this quantity is a negative quantity. So why I consider, if I take a minus sign here, okay, this quantity 2m by h cat square, V0 minus E may be taken as a constant, say gamma square. So this equation now take up this form. Okay, so if you take a solution of this equation, this will become like C2 e to the power plus gamma x plus d2 e to the power minus gamma x. Okay, so these are normal OAB solution, mind it. So if you look at the equation, now it will be like this much. This is your, okay, this is your PN device. If you think in terms of diode, or in general, you can do it for any particle of mass m moving with some energy E along this arrowhead. And this is the barrier height Vx equal to V0. Here there is no force acts on the particle, and the wave function is psi 1, wave function is psi 2. We calculated psi 1 as a1 e to the power I alpha x plus b1 e to the power minus I alpha x. So this is the first one is the whole wave coming in, second one is the whole wave reflected back, and in the region 2 my solutions are like this much: c2 e to the power plus gamma x plus d2 e to the power minus gamma x. Now c2 e to the power plus gamma x, if you look here, you see at x goes to plus infinity, this will go to infinity. c2 e to the power, this will become infinity. So that means it is diverging, so this cannot be an acceptable solution. So this is not acceptable, as I have told you about acceptability of a function. So the C2 has to be 0. So the acceptable part of the solution is on d2 e to the power minus gamma x, because this will be 0 as x goes to infinity. And x, it can become x equal to minus infinity, will become infinity, but here psi 2 is the solution for x greater than 0. Okay, that is the description of the problem, you know. So my acceptable value of psi 2 is therefore d2 e to the power minus gamma x. So if I now progress a bit, you can see, so therefore this is your problem. Okay, the whole waves are coming in given by a1 e to the power I alpha x. Whole waves are reflected back given by psi reflected is equal to b1 e to the power minus I alpha x. Whole waves are transmitted through, okay, that is given as psi 2 is equal to d2 e to the power minus gamma x. Now my job is to calculate, if you look at the whole same thing, my job is to calculate the transmitted incident current density, reflected current density, and also the transmitted current density in this case. Okay, so this is the psi transmitted. So what is the formula? And after that, the ratio of the transmitted current density and the incident current density gives you transmission coefficient. Because the diode is off, so we expect my transmission coefficient should be 0, because I am working here. So let us first verify whether we get this result or not. So it will be last, let me calculate J transmitted. The formula of getting J transmission current density is minus H cut by 2m. Okay, it is quantum mechanical current density, not just classical current density I by A, because here everything is obtained from psi. This is the classical formula. Okay, so this classical formula is not applicable. We are using quantum current density, ddx of psi transmitted minus psi transmitted ddx of psi transmitted star. Now psi transmitted is given here. If you take its conjugate, it is d2 star e to the power minus gamma x. So now if you look at this expression, it is minus h cut by 2m. If you put the value, it is d2 star e to the power minus gamma x, and your value of the derivative will be minus gamma, derivative will be minus gamma d2 e to the power minus gamma x, and the other one is this much. Psi transmitted is d2 e to the power minus gamma x, and the derivative will be equal to d2 star minus gamma d2 e to the power minus gamma x. So if you look at the expression, it is minus h cut by 2m, so it will become d2 mod d2 square minus gamma e to the power minus 2 gamma x, and the other one is basically d2 mod d2 square minus gamma, that is okay, there is a minus gamma is there, so minus plus gamma e to the power minus 2 gamma x. So result, these two are equal and opposite. So result of the net transmission JTR, transmission current density, is 0. If JTR goes to 0, your transmission coefficient will also be 0, and that is the expected result. We do not expect any current, so we get this result. Now there is nothing new. Now the point is that if you look at the description of the problem, is this. This is my This is the whole wave coming in, psi incident, a1 e to the power I alpha x. This is the whole wave reflected back, psi reflected, b1 e to the power minus alpha x. This is the whole wave transmitted through. Whole wave transmitted through is this much. Psi transmitted c2 e to the power minus gamma x. We calculated transmission current density. It is 0. Transmission coefficient is also 0, and producing this portion of the characteristic graph. E less than V0 means I do not expect any current. But you see, I ask you a basic quantum mechanics question. If you look at the psi transmitted, if I ask you to calculate mod psi transmitted square, what is the value? Mod psi transmitted square is mod c2 square e to the power minus 2 gamma x, and you can realize this is never 0. This is basically referring to an exponentially decaying function, but this is not equal to 0. So what does it mean? Mod psi transmitted square is the probability of finding the particle in region 2. In region 2. So the idea is that even if E is less than V0, we find finite probability of finding the particle in region 2. According to the basic quantum mechanics, this is the probability of finding a particle. So the beauty is that there is a beauty waiting for you. Beauty is that if this is my barrier, waves are coming in, waves are reflected back. Okay, but you see, if you look at the transmitted wave for E less than V0, okay, which is like d2 e to the power minus gamma x, what you notice, if I calculate mod psi transmitted square, that is a probability of finding the particle in region 2, even if E is less than V0, you see this value, that is mod d2 square e to the power minus 2 gamma x, that is non-zero. So that means there is finite probability of finding the particle in region 2, even if E is less than V0. Then question is that how is it possible? Because our transmission coefficient, even if, although I have shown you that transmission coefficient is 0. That means we thought that electrons will be moving along this way, but this is 0. So that means apart from this route, there will be some other alternative route by which particles can go here. Now, so there must be an alternating route. Must be an alternate route by which the particle has moved away. Okay, so if you look at the description, that this is the potential barrier, particles are coming in, particles are reflected back. For E less than V0, if it is x0, x less than 0, sorry, x less than 0, x greater than 0, we anticipate nobody will be moving across this path. T is less than T is 0, and this is my IV graph. Okay, because I am living here, E is less than 0, T is 0, no current is there. But quantum mechanics tells me, basic quantum mechanics tells me, even if no particle is going by this way, that there is finite probability of finding the particle. This is non-zero. Now there must be an alternating route for the electrons to go to the, or holes to go to the other side of the junction. This alternating route is called tunneling route, tunneling path, and this phenomena is called tunneling in quantum mechanics. Tunneling phenomena obviously will work over this portion of the graph, and tunneling phenomena is observed in tunnel diode. You cannot see tunneling action in usual diodes, because in usual diode, whatever you see, that this IV characteristic will be graph will be obtained in usual diode. This is the IV graph that you see in usual diode. Here there is no current, no transmission. So for tunneling action, we need a special diode. If I just give an idea what you have to do, so this is the depletion region in normal diodes. Okay, ions are here, negative ions are there, suppose. These are the holes are there, and electrons are here. This is a normal diode. This is your, so what you have to do here, is this much. Okay, this is a normal diode. These are the negative ions, these are the positive ions. These together they are making the depletion region. Okay, x equal to 0, x greater than 0, electrons are here and holes are here. Okay, normal route tells that this is the voltage barrier, it cannot cross the barrier. Okay, the particle do not, this E is less than V0, so they cannot go by this way. Tunneling path is this much. You have to make n to n plus. That means you have to do heavy doping, and p to p plus. So lot of charge carrier will be there, lot of holes you have to inject. So what they will do, they will come into this region. Okay, they will now occupy into this, they will be coming into the depletion region. So what it does, if you look at the picture now, it becomes like this much. In the depletion region now holes do enter, in the electrons do enter. What it does, effective width of the depletion width reduces. So the probability, whatever be the depletion width initially was there, this was the initial depletion width, say W, now it is reduced. So the chance of the holes to cross the junction becomes more, two ways, because their numbers are high, and second is the, because their numbers are very high, this is the effective depletion width. Okay, their numbers are large, and second is that it has to traverse a much smaller length. So basically that's why in this region, at if this is E equal to V0, at E less than V0, this actually you get some current. Okay, this is the action of a tunnel diode. Okay, the details is beyond the scope of the discussion. Okay, so what is the beauty here? IV curve slope is positive, so resistance will be positive. So positive resistance means it refers to decay of current, but here the slope of the IV graph is negative. So if I plot di dv, differential resistance is negative. Differential resistance negative means, okay, here current will be produced. Current is produced, and the device which produces current is called an oscillator. It produces high frequency oscillation AC signal, and this action is called negative differential resistance action. NDR, these are called NDR device. You see the beauty here. Beauty is that, just you see, if I get back to the PPT, beauty is this, just by this is tunneling action. Okay, electrons are coming. Okay, beautiful animations are there. Okay, you see the animations very carefully you see, and this is tunneling through now. Okay, a portion gets reflected and a portion is getting transmitted. Okay, again you see wave is coming in, a portion is get transmitted through, and a portion remaining gets reflected, shown by the various colors there. Okay, okay, this is tunneling. You see that it is coming in, a portion is getting transmitted through, very small portion, exponentially it is decaying, and the portion is reflected back. The blue one is, the red one, you see the pink, the below one, it is portion gets transmitted, a portion gets reflected, and you see this picture. The red one is the red ball, you see, it is basically referring to matter. Okay, it is coming, a portion gets transmitted and a portion gets reflected, and that is all about tunnel diode. So it's an alternate route by which electron can move. It is applied in this device, tunnel diode, that is called negative differential resistance device. So it concludes our discussion on the problem 2 of quantum mechanics. One more problem is left out with. So next day we'll discuss the third problem of quantum mechanics. So please keep patience. Thank you.